So that brings us to the next and final point. How do you actually build these things? Our current quantum computer designs consist of two main types for construction: the superconductor type and the spin type, that is, the use of small particles. The most popular spin method uses single electrons within silicon to create qubits. The reason for this is that the infrastructure for nanoscale silicon components is already established, so it makes economic sense to just leverage what we already have for a new kind of computing. These electrons within the silicon are called quantum dots. Only several nanometers in size, they can operate at slightly higher temperatures, making them more stable. Research on this method only started to pick up in 2017. The older, more established qubit uses a metallic superconductor to create a quantum state. Superconductor qubits defy the misconception that the strange quantum effects are impossible for larger objects. This is not strictly true. The way we get large objects to produce quantum states is by letting the material reach that fragile diva state. This is done by subjecting them to a super cold vacuum environment. The result is a qubit that's visible to the naked eye. The most popular method is a super cold metallic ring, almost at absolute zero. At these temperatures, electrons can flow around forever without ever bumping into anything. Stranger still, all these electrons flow clockwise, but at the same time, all the electrons also flow counterclockwise. If the clockwise flow is read as a 1 and the counterclockwise flow is read as a 0, it's essentially a superposition qubit. The superconductor method is how D-Wave, IBM, and Google quantum computers work. So to round out, let's take a look at a few achievements. So right now, the best quantum computer we have is using the quantum dot method, though most of those qubits are used for error detection. On the road to building a quantum computer, MIT scientists have reported the discovery of a new triple photon form of light. An Australian team has set the record for the most accurate 1-qubit gate in a silicon quantum dot. They had a remarkable accuracy of 99.96%.